All right. Good morning, everybody. We're going to really change gears in a big way in this course starting this week. Up till now, it's been all circuits with, programming that barely felt like programming, right? It's closer to the circuit level in a way. From now until the end of the semester, we're programming. And I'm going to give an overview of what that programming is going to consist of. I want to emphasize right from the start that you will be able to use any programming language you want from here on out. There's no specific language required. The only thing is if you use something really obscure, let me know the instructions to install the compiler on my machine so that I can, grade it. Aside from that, you can use Python, Java, Haskell, Rust, any language we've covered, or if there's some other language you're familiar with that you just can't wait to try out, that's fine too. It's just whatever works for you, really. So, in thinking about this then, what I want to do is sketch out what are these projects going to look like, and in what way does it make sense that you can use any language you want. So what we're really doing at this point is building a compiler. All of the projects we're about to undertake culminate in the creation of a compiler, with two exceptions. You're going to have one project where you write a program that gets processed by the compiler. So you're going to, much as before you built the CPU, you wrote a machine language program. Before you get to the final stages of the compiler, you're going to write a program in their made-up language called Jack, which is a thinly disguised version of Java. And then chapter 12 is going to be writing some pieces of the operating system. So specifically, you're going to write device drivers for the keyboard and screen, some memory management. You're actually going to implement a lot of common mathematical operations that weren't actually put into the CPU, that sort of a thing. It's like multiplication and division and so forth. That'll be chapter 12. Some of the projects we're going to be doing are pretty hard, and so I've actually taken some of the chapters and broken them up across multiple weeks to try to give you a little more time to get those done. That's just based on my experience in the past. The first time I taught the class, every chapter was a week, and one reason I compressed and accelerated this first part was to give you more space to work on the second part, which is harder than what we had been previously doing. So let me go ahead and outline these stages for you. So we're going to be working on today is chapter 6, which is creating an assembler. Chapter 7 and 8 is creating what's called a virtual machine. So what's the idea here? In practice, it's a lot easier when building a compiler to have some kind of intermediate language that's halfway between the source language and the raw machine code. And so chapters 7 and 8 involve us constructing such an intermediate language, a virtual machine. So in many ways, it winds up feeling a lot like machine language, but it's definitely higher level. It's going to have things like functions and returns and so forth. And it'll, generally speaking, be higher level. This virtual machine is going to be what's called a stack-based language. So, like, everything you remember about stacks from data structures, we're just going to be amping that up massively. You all are going to be stack virtuosos by the time you're done constructing that. So in chapter 9 is where you're going to write a Jack program. And that's going to be a really free form assignment. That's on the level of pick something you think would be cool to do and do it. Then chapters 10 and 11 are the full-blown compiler. And I'm experimenting this semester in rearranging the material to make it hopefully a bit easier to complete based on and compared to what I've experienced in the past. So we'll be going through that very, very carefully. And effectively what we're going to do is do it the way compilers tend to be done in practice, which is get the compiler working for like the simplest possible program, and then gradually add more and more of the language to it. So it'll just kind of grow on outward from there. And so what happens is then the compiler generates virtual machine code. The virtual machine translator generates assembly code. The assembler generates ones and zeros. And so that gives us that end-to-end process of translating a program into something the CPU can understand. You know, something we talked about a fair bit when we were working on the CPU is the idea that how the instructions work is totally arbitrary, right? There's nothing that happens that automatically forces them to have this particular bit pattern or this particular approach or whatever. We design the CPU and we make up the meanings of the bits. You're going to feel this even more strongly as we work on the compiler. That is, why does a while loop work? It's because you describe what it means to be a while loop in the virtual machine language. And that's all. You know, you could define it differently and it would be different. That the language has any meaning at all is only because you impart that meaning in the compilation process. So pretty cool, kind of a big deal. Any questions about the overall direction of where we're going before we begin thinking about building an assembler? I sense a question.
You mentioned that you can use whatever language you want.
That's right.
I am just trying to think, is an assembler going to be like any sort of like random Python program that has a main function, a couple functions connected together that does things?
Yep. I mean, the way you can think about it is what the assembler does is in generating the machine language program, you can imagine it as burning a cartridge that you can insert into this machine. And in effect, that's what our compiler will do. It will take a high-level program and effectively burn a simulated cartridge that you plug in and then set the machine going. Yeah. But yeah, you can use Python, Java, whatever. Haskell, Rust, any of the languages we've looked at. Or if you're like super eager to try, you know, some random language, that's fine with me as long as I can get a compiler for it easily installed on my machine. Odds are, if you can do that, I probably can too, but I'd like to at least know like the website to download it from and install it. So, yeah, so that's that. Cool. Any other questions so far before we begin looking at the details of how to build an assembler? Okay, time to build an assembler, or at least think about it. So let's think about what an assembler does. What, at a high level, is the operation it performs? You can think of an assembler as a function that takes a source program and then generates what we call an object file. So you've got a source file and an object file. The assembler takes the source file, spits out an object file. So to get started on an assembler, and I've noticed in the past, this is where students often struggle quite a lot, is I'll have a student just say, I'm trying to work on the assembler. I don't even know how to get started. So I'm going to answer that now. The way you get started is you can write a program that just takes some kind of input file and then just echoes it back out, right? So if you can at least write a program that reads in a file and spits it back out, that's the start of the skeleton of the assembler. Now you notice if it just reads in a file and spits it back out, it hasn't really done anything. And that's true, but sometimes part of what's intimidating is trying to figure out, well, what's the overarching structure of what my main is doing? So if I can read in a file and spit it out, well, so much the merrier, right? So what we're going to do to kick things off then is I'm going to open up PyCharm and I'm going to write a Python program that does this. Hopefully, at least for some of you, it'll be a nice memory refresher. Whoops, didn't mean to do that. Nice memory refresher of what it even looks like to write a program that does that. You know, it turns out in Python that is relatively easy. So let's wake up PyCharm. Yes. Yeah, it's setting everything up. Yeah.
PyCharm is coming.
Mostly Python and Java. Yeah. Yeah. Oh. Yes. All right, so I've got a Python program. I want to read in a file. So I'm going to just start by writing a function, and I'm going to call it assemble. Oh, the font is probably beyond unacceptable. It's pretty bad, Blake. Yeah. All right, so let's just quickly go to settings or view appearance. No, maybe it's settings. Maybe it's editor. Maybe it's font. Yeah, this is promising. All right. Right now it's a 13. Let's go to 16. Do we need to go a little bigger? Okay. So let's go back to settings. We're going to try 20. How's that? All right, cool. So, of course, in order to assemble, I need to know what I'm assembling, right? So why don't I just go ahead and say file name. So now what I'm going to do is read in the file. So file in equals open file name, comma R. So that's how you can open a file for reading in Python. And then you can read the whole thing into a string. So you can say something like file contents equals file in dot is it just read? Yeah. And then you can tell it to close. You're done with it. So now we want to write a file to output. So the input file should have a .asm suffix, and then the output file should have a .hack suffix. So what we can do is something like this. We can say something like file stem equals file name dot split on the dot. And then we take element 0 of that list, and we can say output file equals file stem plus dot hack. Then we can say file out equals open output file dot output file comma W. So now we've got something we can output. So then we can say file out dot write, and I'm going to pass in the file contents. And then I can say file out dot close. So I've assembled, so to speak, a file. So let's say I want to test this. So I'm gonna, let's, it's a traditional little Python guard thing. So if name equals main, here, let's do this. We'll say file name equals input, enter file name. And then you can say assemble file name. All right, it's not pretty, but it'll do. So I don't happen to have any ASM sitting around, so I'm actually going to tell it to assemble itself. So now I have ASM demo.hack. And when I open it up, for some shocking reason, it looks identical to my source file. So let me review how this worked. So the only reason I switched the tab over was to get my syntax highlighted, because they were otherwise identical, right? So say I want to read a file. I can read the entire file into a single string, close it. Then I need to create the name of the output file. So I do the split, bracket 0, output file equals file stem plus dot hack. So notice my ASM demo.py became ASM demo.hack right there. And then I use write to write the whole thing up, close it. When you run it, it asks me for the file name. I give it, life is good. So pretty straightforward to, at the top level, have a skeletal way of saying I can read in a file, I can spit a file out. Any questions so far? Okay, let's think a little bit more then about the next level, the next aspect of thinking about things. So something that we have discussed is the fact that in thinking about what an assembler does, each assembly language instruction becomes one machine language instruction. So setting aside the issue of labels and comments, which are important, but we're just going to disregard them for the moment. In effect, we can read in one line at a time, and every time we see a line, we know we should be spitting out a machine language instruction. So, you know, the design of our program is basically to say for each line of input, output the assembled line. So, obviously, I don't want to teach you all how to do this by giving you a complete hack implementation. What I do want to do, though, is make sure that you've got an idea of what an assembler actually looks like. So to that end, we're actually going to build a simple assembler for the Turing machine CPU we designed last week. So let me review with you our instructions, right? So we have ML move left, and that's 1, 0, 1. MR move right is 1, 0, 0. We have jump if the tape is clear, and that was 0, 1, 1. We have jump if the tape is set, and that's 0, 1, 0. And then we had write the tape, 0, 0, 1, and oops. And just as I just did, we have erase the tape, and that was 0, 0, 0. So we can imagine building an assembler in terms of, for each of these instructions that we encounter, we emit the appropriate bits that correspond to that instruction. So let's imagine what that's going to look like. So if I come back, oh, sorry, wrong editor. So if we come back here, we can think about the underlying structure of what we might want to look at. And something we might notice about that structure is that in this example, we read everything into a string at once. We can see, though, that there might be value in reading one line at a time, since we're reading in one line and we're spitting out one line every time. So to that end, I'm going to rearrange this code a bit. The first rearrangement I'm going to do is I'm actually going to open our output file very early on. So I open my input file, I figure out the name of my output file, I open the output file, bam. And so my strategy is to read one line from my input file in at a time, and then immediately write the assembled line to my output file. Okay, so let's imagine what that's going to look like. So in Python, you can iterate through a file by saying for line in, file in. So it's creating what's called an iterator that does a complete pass over the input file, but one line at a time. So for each of these lines, so let me clean up some things we're not going to be using, like so. And of course, when we're done, we will want to close both files, so that's not asking too much. So for each line, I want to assemble it. So as I assemble it, I think, well, for each of my instructions, there's like a collection of bits that corresponds to it. So kind of a fun way to do this then is I'm actually going to build a dictionary that defines them. So what would be involved with that? I can say something like instruction 2 bits equals a dictionary. And so in this dictionary, I can just set up some key value pairs. So that one is 1, 0. Ah! Okay, I clearly mistyped something. Editor basics. Okay, I'm glad I got that cleared up. Yeah. All right, so and there. Okay. So move left is going to be 1, 0, 1. And then move right is going to be 1, 0, 0. And jump clear is going to be 0, 1, 1. And jump set is going to be 0, 1, 0. And then right is going to be 0, 0, 1. And erase is going to be 0, 0, 0. So the first thing you might notice about this that might seem initially a bit odd is that even though the output machine language instructions are fundamentally numerical, I am encoding them as strings. And there are several good reasons for this. First and foremost, yeah, they might be numbers, but I'm not actually using them in a numerical way. You know, I'm not going to do any math with these things. Secondly, What I really care about then is how does it get put into the output file? And really all I want is a string, which leads to the third consideration, which is if I represented it numerically, I would lose my leading zeros, which is going to be part of how the simulator we're working with processes them. Now, this is, in a sense, artificial compared to like a real assembler. And what I mean by that is a real assembler literally outputs the bits as numbers to the output file. The result is an output file that looks like complete gibberish. Because if you open it up in a text editor, say, you just get all of the random Unicode characters that correspond to the bits you emitted for your instructions. That would make this needlessly difficult to debug, I think it's safe to say. So we're going to use this very simple format as a means of representing the machine language program. Well, at this point, the program practically writes itself, right? I can say file out dot write instr to bits of line, and I need to use the strip method to get rid of any white space, tabs and new lines, and so forth. And then once I've got that, I will add a new line character so that it actually goes to the next line. Yes? That's an excellent question. For now, what's going to happen is my program is going to crash. Now, here's the really important news. For all of these programs you're going to write in the compilation process, there is no requirement for you to do any error handling whatsoever. Now, in a real assembler or a real compiler, do you have to do error handling? Yes. That's really part of a compiler's job, is to help educate the programmer about what a correct program looks like. If there's an error, the compiler needs to help the programmer to find it. If it doesn't, the programmer is going to stop using the compiler. And rightly so. Rightly so. It's just, the compiler smacking you in the face and saying, wrong. Try again. Wrong. Wrong. Nobody wants to use that, right? But the purpose of this assignment is not so much for you all to write production-ready compilers. It's not the purpose at all. The purpose is for you all to learn how higher-level abstractions get mapped down to lower-level abstractions. And so to that end, not worrying about errors is actually fine. Weird though it may sound. So I'm now going to do the next step, which is we need to write a program to translate. The program really doesn't need to make any sense, but it does need to be something that can be reasonably assembled. I don't want a scratch file. I just want a file. Yeah, I just want a new file. And we are going to call this file test1.tm. TM for Turing machine. Yeah, and we're just going to call it a text file. All right, so we're just going to put together a simple program. So let's say we write, we move left, we write, we move right, we erase, and then jump if clear, we write, we erase, something like that. Obviously, this isn't much of a program because we haven't even implemented address register stuff, but it's enough to have a basic test of our assembly. So I go ahead and save this, and now I'm going to run my demo. So I'm going to give it test1.tm, and now test1.hack has been output. And check it out, we have a bunch of machine language instructions. Yeah.
So in thing about
Mhm.
so we need to have a giant map as well to sort of encode every possible operation that our CPU does, so we can read into its corresponding like machine language code.
That will work for the hack machine. That's more work than you strictly need to do. So let's talk about why that's the case as we think about what this is going to look like. Let's review what a machine language instruction looks like for hack. We're going to disregard the A instruction for now. We're going to focus on the C instructions. So you have 111, which is just the, hi, I'm not an address. Then you've got your A bit. Then you've got C1 to C6. Then you've got your destination bits. And then finally, you've got your jump bits. Now, in principle, you could imagine working out the bit pattern for every possible C instruction and putting that into a map. In fact, you may choose to do that, and I will consider that a correct solution. But you may find that it's a bit less work to think about it in a more modular way. Here's what I mean. So typical instruction might look something like, D equals M plus D, right? Now, again, one way I could encode this is to have a dictionary key for this precise instruction that then corresponds to all of the necessary bits. But I'm going to suggest there's a better way to do this. And here's what I mean. I can have some if statements to classify different instructions in different ways. For example, I could say something like this. If the instruction has, an equal sign in it, okay? What I can do is I can do a split, so I can break it up into some parts, or I could say something like this. I could say, parts equals instruction dot split. That was terrible. Let me rewrite that. Split on the equal sign. Okay? And so then what I could do is have a dictionary that gives me the C bits for the ALU output. Right? So I might then have in assembling my output, it could look something like this, right? I could say, first I need to figure out one way that might be easier is actually have it be A and C1 through C6, so 7 bits, because what A is depends on whether you've got an M or a D, or an M or an A over here, right? So you could just do it like that. So I might then say, the output line is going to be something like 3 ones, because it always starts with 3 ones. And then I might have my ALU map, and so I say ALU of parts bracket 1. In other words, when I did my split, I was able to break it into the D and the M plus D. I could then have a dictionary that examines M plus D as these bits. And so that's the ALU part of what I'm doing, right? And then maybe I've got another dictionary that then decodes the destination, right? And so then I say something like plus dest of parts 0. And there are 8 distinct possibilities for the destination because it can go to D, it can go to M, A, or AMD, and so on and so forth, right? And so now I've put together, most of the instruction. And there might be other ways you could break this up because, of course, you got to take the jumps into account, right? So, at some point you then need to say, if the instruction has a semicolon, then you say, okay, well, line plus equals, jump of the part after semi. So, this is just giving the basic idea. You can't directly use this as your logic. Really what you want to do is before you even get into the decoding, you just want to split everything into pieces and know what you've got for each piece. And then from there, you just get to put an instruction together. Now, in the case of the assembler that I just built, that stuff doesn't really matter very much. And the reason it doesn't matter very much is that the instructions are so incredibly simple, right? There are only 6 instructions. So you just load them up and go from there, right? But if you think combinatorially about what you get combination-wise with everything that Hack lets you do, if you were to specify the bits for every possible combination, it would be a rather large amount of work. Again, if you do that, you're going to get full credit for the assignment. I'm proposing a scheme like this to save you work in working out what the underlying bits are going to look like. But if you want to brute force it, that's fine with me. But I can see you shaking your head, Innocent. I suspect you rather do not. So that's kind of the heart of doing the assembler right there. Any questions so far before we begin looking at some other aspects? All right, let's look at some other aspects. So again, I can come back here and show you my assembler, and it's like 11 lines of code. Now, for this assignment, you're going to write a bit more than 11 lines. Kind of sorting out those different pieces and so forth is going to take some effort. But even this one is ultimately going to need to be more than 11 lines. And so let me show you why. If I come back to my input file, and let's say I want a comment, like so. And let's also say I want to have some blank lines and that kind of a thing. Well, I'm going to have to take care of this, right? So what does it look like to do that? Well, I can just come back here. Whoops, I didn't mean that here. I can come back here and recognize, maybe this was just a little too simple-minded, right? So I can do something like the following. I could say my instruction equals line dot strip. And then I might do something like the following. I could say something like, if the length of my instruction is greater than 0, well, now I can actually, do something, right? See, if its length is 0, so I've done strip, that gets rid of white space, it gets rid of new lines or whatever. So if there was nothing but spaces, I'm done. So now here's something else I can do. See, I also need to get rid of comments. So to that end, even before I get to this point, I could say something like this. Let's say no comment equals line dot split on the double slash, the comment instruction. And then after the split, I can say I only want stuff that's before that. And then I can say, let me take no comment dot strip. So let's try this out. And if I look at test1.hack, there it is. So a lot of what you're doing then in building an assembler is fundamentally just a bunch of text processing. Right? And that's going to be the case for every single stage of the compiler. At every stage, you're doing a bunch of text processing. And that's at the heart of what it's about, is examine the text and find the meaningful content within that text, and then act upon it in a suitable or appropriate way. Any questions so far? So now our assembler is up to 15 lines. Oh, it doesn't need to be quite that long. I have maybe one blank line too. But yeah, with just a couple of careful pre-processing steps, we can banish all comments and all blank lines because we just don't care about them at all. Any questions? Any questions? So we've now got a skeleton for a compiler, an assembler, sorry. Well, let me do one more thing, just demonstrate that this works. So I'm going to put a comment. And I just want you all to see how nicely this works. And test1.tm. Whoops. I got a key error. Oh no. How did I get a key error? Time to do a little debugging. That's okay. Come back, error message. You go away. How did it get that far? Should have done a split right here. It's okay. We're going to do a little debugging. And we're going to try it again. Oh, yeah. Here was my problem. After all that, I'm still just using line.strip over here. Yeah. So what I actually need to use is instr. Okay, now it worked great. So I had all the pre-processing right. I just missed a certain key step, which was actually use what I did. So there we go. Yeah. I just had an intuition that somehow had to be tested. All right. So this is pretty cool, right? It's really very straightforward to build an assembly. You just walk through it, parse stuff out, start putting it together. So, any questions so far? Okay, so let's talk about a few other aspects of doing this. So, at some point, you also need to handle the A instruction. I'm not going to do an example of that, even though it's an intrinsic part of this Turing machine architecture. But I'm going to talk about what you're going to need to do when you encounter it, right? So early on in your assembly stage, you're going to need an if statement of some kind to see if it starts with this @ symbol, okay? So let's say it starts with the @ symbol. So now what you need to do is, grab the address, which will be like some kind of slice of the instruction without the @ right? So you've got this Nice numerical value. The next thing you're going to have to do, tell me, what's the next thing you're going to have to do? Convert it to binary. Yeah. If you're in Python, I think Python has some kind of a built-in method to easily do this. Let's say you're using Java and it doesn't have that. Well, what does it mean to convert a number to binary? What does that look like in a fundamental way? So to do a conversion to binary requires figuring out what do you get every time you divide it by 2, right? So let's imagine what something like this will look like. So let's imagine I want to convert the number 5 to binary. So first, let's think about it in human terms, and then we can imagine what it looks like more mechanically or algorithmically. So looking at this, just humanly speaking, how do you start? Well, let me rephrase it. What's this in binary? What's that? 101. So Andre, how did you get that?
I got the largest bit, actively go over, and then keep going until I'm trying to find the next bit that'll add to it, actively go over.
Mm-hmm. Yeah, pretty much. So let's imagine what this is going to look like. Let's imagine for this instance, what we have is a 4-bit unsigned value, okay? So we've got a 4-bit unsigned value. I could imagine having a loop, and in this loop, I would, every time I go through this loop, I'm going to add a 0 or a 1 to my output, okay? So I'm going to initialize this loop with the value of the largest possible bit. So if it's a 4-bit unsigned value, what's the value of the leftmost bit? So here are my 4 bits. I want to give each of these a value. I want to know what this is. So why don't we start over here and see where we get. What's the value of this position right here? Good. What's the value of this position? Next one. And this one. 8. So if we follow what Andre was suggesting, which is a sound idea, we have some variable that we initialize to the value of 8. Then inside of our loop, we're basically saying, you know, while this var is greater than 0, right? So while it's greater than 0, we take, you know, and we've got, you know, some variable for the instruction is an empty string. And then we've got our numerical input we're looking at. So you'll definitely use some kind of operation to turn a string into a number. You know, like in Python, it would be the int function. And you basically say, you know, while that variable is greater than 0, you find out something like, you know, if, you know, the num is greater than the var, well, num equals num minus var, and our instruction plus equals, you know, the 1 character. Otherwise, our instruction plus equals, you know, the 0 character. Now, to keep the loop moving, what else do we need to do? Incrementing, I would argue, is not the right idea here.
Maybe decrement. There is have to be a change.
There's some kind of incrementing.
Yeah.
let's look back at this progression. What kind of change do we need? Right, we actually need to divide by 2. So you'd have something like num / equals 2. In Python, of course, you want that to be a double slash for the integer division. And so, yeah, hand coding a little decimal to binary converter isn't very hard. You can certainly do that. But there's another aspect of this that we haven't really talked about that involves some careful thought to get right. What do you all think I'm referring to?
If you type in at like a word, assign it to 16.
Labels. Yeah. So labels are very, very important in an assembler. Very, very important, okay? In fact, labels can make an assembler quite a bit more complicated. And the reason they can make the assembler more complicated is that to resolve labels, the easiest implementation strategy is to use 2 passes. So what I mean by 2 passes is you do a first pass where you build a symbol table and resolve all the values of the labels. And then you do a second pass where you fill everything in. Now, why might you need to do something like this? Well, as you're writing an assembly language program in Hack, sometimes you might want to do a forward jump, right? So you set your address register to some part of the program that's further down than you've processed so far. Well, if you haven't seen it, you can't do it, right? There's no basis for that. So the solution is to use 2 passes. So, and if you use 2 passes, certainly as you go, you'll be wanting to build a data structure that stores the instructions that you want to process on the second pass, right? So you could like use a list, for example. So, I showed you that assembler. It was pretty simple. Yeah, they get more complicated. But I wanted you to see the stages of how we get there, right? In principle, you can have a working assembler with no labels, right? You can hand calculate the jump targets and so forth, and it'll work. It'll be fine. Will it be painful to use? Yes. Would anybody ever program with it? No, you need labels. Yeah. And a lot of the value of labels is it greatly simplifies the later stages of the compilation process. So if we look back at the stages of what we're doing, the assembler, by having labels, makes it easier to create a correct virtual machine. The virtual machine can emit labels right and left, and then it's in good shape. Really simplifies that process. So this is where the complexity of labels belongs. We need to handle them in the assembler, okay? So on the first pass, and I'm not going to be coding a demonstration of this. This is something you all really need to do. But given what I've coded for you, I think you can begin to see how this all fits in and what it looks like, right? So on the first pass, we're going to build a symbol table. So what does that wind up looking like? Well, as you all know, we've got multiple ways of defining the value of a symbol. It can either be an address in the program memory, or it can be an address in RAM. And we can't immediately figure that out until we have gone through the whole thing, right? So what's this going to look like? Here's my suggestion for how you might go about this. So anytime you have an at with some label, actually, let's not do this first. we're going to start with the labels themselves. So syntactically, a label is denoted parentheses, label, close parentheses. So for each of these, you know what number it corresponds to based on which line of code you're on. That means that you're going to need some kind of variable that is tracking your line number. I need to be really careful with this because blank lines, comment lines, and label lines aren't actually part of the generated code, right? So they don't get line numbers. Line numbers only apply to actual machine instructions. So you don't want to increment this line number variable until you've encountered an actual machine instruction. So let's assume that your line number variable has been updated properly. What you can do is you can put in your symbol table, and for this I recommend a dictionary or a hash map or whatever, right? So you say something like sim of label. Whoop, okay, that was beyond. Whoa! Okay, let me try that again. No, that. Yes. Okay, sorry. Let me do a little bit of erasing. Okay. So you say sim of label equals that current line number. Okay, that's pretty good. Now, that's kind of the first situation. The next situation is you have something like at label. So what's complicated about this situation is that there are two possible outcomes. The first outcome is that it's a reference to some kind of line number in the ROM. The second possibility is that it's RAM. And within that first possibility, there are two more possibilities. We're going to make a chart. Okay? So, first possibility is line in program. A is already seen, and B is unseen. And then 2 is that it is in RAM. Okay? So these are the three real possibilities. Okay? We need to code each of them differently. The easy case is this one. Why am I calling that the easy case? You can, yeah, that's exactly right, Innocent. You just ask your symbol table if that label is already a key. If it is, great. You look up the line number from the symbol table, and you can immediately then transform it into binary, and life is good. What about the other cases? In those cases, well, actually, you're not even doing that yet, right? Because we're on the first pass and we're not generating anything. I zoomed ahead a little bit. Forgive me. So it's already seen. We don't really have to do anything else at this stage. Why? Because the label is in the symbol table. If it's unseen, we're going to have to somehow keep track of the fact that we saw it. But keeping track of the fact that we saw it in some way that kind of lets us go back and resolve what happened, right? And really the same thing applies for this 2 situation, the RAM. You've seen it, but now you need to think about how do I keep track of them? So you might remember you're going to generate these things by the first one you saw is 16 and the second one is 17 and blah, 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 and so forth. So here's what I suggest. In both of these cases, put them in a list. Okay? Just stash them in a list. Then, after you're done with everything, it comes time to add everything from the list into the symbol table. And so here's what you can do. You can say, for each label in your list, what you're going to do is say, if it's not already in my symbol table. So if it's in my list, but it's already in my symbol table, that means ultimately it was found to be a label somewhere later in the program. So what you do at this stage is you just ignore it. You just don't do anything with it. Otherwise, you've got some counter variable, which you might call ram var, and then you set it initially to be 16. So if it's not in the symbol table, you say sim of label equals ram var, and then you just increment it. Like that. And you just keep trucking along. And so at this point, you've got this very nice symbol table. And now you're ready for the second pass, right? Because let's see. Yeah, first pass. Bam. Second pass. And this is just our plain old assembler. And then just look up your symbols as they arise. Now, something really important in the first pass that I didn't make extremely explicit is that you're going to be building a data structure, probably a list that contains actual instructions. So every time you see an actual instruction, you put it in that list. In fact, that can even replace the need for a line number variable. You can just use your instruction list and ask for its length. Yeah. So that's a nice little shortcut that one could do. So in the second pass, it's just your plain old assembler going through this list, and then every time you have an at with a symbol, you just look up the symbol in the symbol table, get that value, convert it to binary. Bam. You're done. And now you've got a beautiful assembler. So cool. Any questions up to here? Any questions? Makes total sense. Total unmitigated sense. All right, great. So another detail of considerable importance is the following. There are going to be predefined labels. So let's see. I'm trying to remember. Oh yeah. So the predefined labels are given on page 110 of your book. So what are some of these? You used them, right? So KBD, screen, SP, LCL, ARG. Okay, some of these you haven't used, like this and that. And then R0 through R15. So those are all given on page 110. And really all you need to do is preload your symbol table with those values. Right. So when you set up your symbol table, you just load it up with those values. And bam, you're good. Yes?
Do you also have like their corresponding binary representation?
I would just use an integer for them, because whenever you get something out of the symbol table, you're going to convert it to binary. Or, you could do it that way. Admittedly, you could just have your symbol table mapped directly onto the binary values and do the conversion when you put it in. It really doesn't matter. You can convert when you put in, you can convert when you take out. Now that I think about it, if you're deeply concerned about efficiency, which for this assignment you shouldn't be, it's just not really the point of the assignment. But if you're going to retrieve it more than once, it's kind of worth turning it into the binary value when you put it into the symbol table. But doing it then or the other time has no effect whatsoever on how I am going to grade this assignment. So The emphasis on this assignment is strictly on correctness. Does it correctly assemble the given files? That's all I care about.
This maybe the question I have is, you say you can load the symbol table and let's say put KBD there.
Yeah.
Enter one, screen enter two. And like, are those like integers just supposed to be that arbitrary, or they're supposed to be some integer that corresponds to some binary number that corresponds to the KBD?
Got it. So you remember in making your CPU that you wired the memory chip so that the keyboard is at 24,576. That's intrinsic to how it was wired. Consequently, this KBD variable had better be 24,576. If you want it to, work. Right. And why does it need to be that? It's because it's how it's wired. Again, it's an arbitrary choice, but the thing about these arbitrary choices is once we've made these choices, we then need to be internally consistent about how we use them. So once you've wired the keyboard to 24,576, any program that dares to read the keyboard had better be reading 24,576. Excuse me, or it's just not going to work. Some of these other symbols are set up to make the construction of the virtual machine simpler. In other words, there are going to be things the virtual machine needs to be doing where it's going to have to be emitting stuff for SP, LCL, ARG, this and that. Just to give you a hint as to what that's like, each of these is going to be a reference to a region of memory that has a particular purpose. For instance, SP, that's going to be a reference to the top of the program stack that you're going to be engineering. LCL, that's a reference to where the current function's local variables are in memory, and so forth. This is going to be a reference to the address of an object that you've compiled, and you need to start looking at its instance variables. ARG, any guesses on ARG? What's ARG probably pointing to? The arguments of a function. Yep. That is going to be pointing at an element of an array. So when you've done an array access and you calculate the memory offset, it'll be stored in that. So that's why those symbols are there. When you're working on the virtual machine, it's easier to think at that level of abstraction than just throwing those numbers in everywhere. And because you're going to have this, beautifully working symbol table, might as well use it. So cool. So that is our assembler in a nutshell. You should be pretty familiar with the assembly language machine language relationship at this point, from having written the assembly language program and having created the CPU. So in a way, what this assignment does is it bridges together projects 4 and 5 into project 6. Oh, I should mention this. We do have a test coming up. So let's talk about that ever so briefly. Assuming I can find my browser. Oh, there we are, browser. Okay. So let's look at our schedule. Oh, yeah, there it is. So a week from today, so on the 25th, we'll have a midterm exam, and it's going to cover the first half of the book, chapters 1 through 6. So on Thursday of this week, I'll begin class by answering any questions you have about your assembler, which I strongly encourage you to be working on. I am also going to review for the midterm. Now, what form is that going to take? If you go into Moodle, if we were to log into Moodle, and look at this course, I have put up in the examples section midterm practice problems. So there's a PDF document there. And what I would like you to do is between now and Thursday, print this out, sit yourself somewhere without any resources, and attempt to answer every practice problem. Then bring it to class with you on Thursday. And what we're going to do is I'm going to walk through the problems and I'm going to ask you all for your solutions. Anybody who attempts every solution on the practice problem and brings it with you to class on Thursday, I will give 10 points of extra credit for the midterm. This is meant to be an incentive to help you prepare well in advance and to think about what you need to do to be prepared. Okay. So Thursday, bring it to class, 10 points extra credit if you bring it and you've at least attempted every problem. Okay. And it's fine with me if after trying and something doesn't work out, going back to the book and looking stuff up. This isn't sort of an academic integrity thing, but for your own benefit, I think you get a lot out of running a practice initially and getting a sense of this is what I know, this is what I don't know. And so, yeah, so we'll go over that on Thursday, answer any questions you have about the assembler on Thursday. And then next Tuesday will be that exam experience. And just to give you a sense from there, on Thursday, we're going to start the first part of the virtual machine. And we're going to start thinking about that stuff and just see where we go from there. All right, any questions? Any questions? Okay, I'm looking forward to seeing how your assemblers turn out and reviewing with you for the test next week. Have a great day.